Okay, it says here the imaginary number is defined by. So here's the definition. It's written underneath on yours, but I don't like the way it looks. So we say the imaginary number I is equal to the square root of -1. That is our imaginary unit. Now let's do a little manipulation to see what happens. So what if I took I and I squared it? That is just going to be -1. It's going to be a square root times a square root. So we know that I squared is equal to -1. Now what about I to the third power? Well, that's going to be I squared times another I, right? So this is going to be negative square root of -1, which we can write as negative I, right? So that's where we get I cubed is equal to negative I. And then I to the fourth, the way I like to think about I to the fourth is that's an I squared times an I squared, which is 1. But it's a cycle, right? When I was first explaining, I was just given, here's the cycle, and memorize it, right? I like to show where it comes from because it's not just made up. Think about what happens when you really multiply those things together, right? That's where you get the values. And then, of course, I to the fifth, well, what would that be? That would be I to the fourth times another I. So that gives me just I, right? So you start that process over. I to the fifth is I, which means I to the sixth is -1. I to the seventh equals -I, and I to the eighth equals +1.
So technically, you could say that I to the fifth really equals square root of -1.
Yeah, that's what I to the fifth is equal to, the square root of -1, which is equal to I again. We always relate them back. Right, that pattern continues over and over and over. And sometimes you'll see that pattern begin with a 0 power. All right? Well, what is anything to the 0 power? 1.
Cool.
So again, that's where you go back to that. I mean, the pattern still holds. Right? Okay, so right here it tells us a definition of a complex number. It's the set of complex numbers is a set of all numbers in the form a plus bi, where a and b are real numbers. So I talked about before, a complex number is all of the real numbers and imaginary numbers together. So a complex number looks like this: a plus bi. We call the a the real part of the number, and we call the b the imaginary part of the number because it has the I. It's the imaginary unit. It's the square root of -1, right? So they each have a part, and we'll talk more about that as we go. All right, but let's just start here. First, example 1, standard form of a complex number. Determine whether each complex number is real or imaginary, and write it in its standard form, a plus bi. All right, so if I look at the number 3i, would that be a real number or an imaginary number? It's going to be imaginary. And if I wrote it as a complex number, what's the real part of that number?
0.
0. It's not there. Plus 3i. That would be how we'd write that complex number. 0 plus 3i.
So write the standard?
That's the standard form, yes, of a complex number. Okay, 87. Is that a real number or an imaginary number?
Real.
It's a real number. So if I wrote that in complex form, that would be 87 plus 0i. Because think about what is 0 times I.
0. So it's really just 87.
But all of our numbers you've ever worked with have an imaginary part, but that imaginary part is 0.
That is awesome.
Well, thanks. C is 4 minus 5i. Now, is that a real number or an imaginary number?
Both.
Well, it's both. So I don't know how that thing's going to answer. I would just call that a complex number. Your homework may ask you to list both. I don't know. but it has both parts. And so if I wrote that as a complex number, it just is what it is. 4 minus 5i. And then the last one, just the number 0. Is that real or is that imaginary? It is real. And how would we write that in complex form? It is 0 plus 0i.
Okay,
So right here is a little, the key term thing that they show of, like in your textbooks. If you look, the definition, if you add, subtract, and multiply complex numbers. So it says if a plus bi and c plus di are complex numbers, we define their sum, difference, and product as follows. So this looks a little confusing, but look, here's a complex number. Here's a complex number. And I'm told to add them together. Well, guess what you do? You add the real number parts. You add a and c. And then you add the imaginary parts, b and d. Just like terms, right? When you're used to adding 4 plus 5x plus 6x. Well, you combine the 5x and the 6x because those both have the same, they're like terms, right? They both have an x. Same idea. If it has an I, it's an imaginary part, you can add those together. If it doesn't have an I, then it's the real part. You add those together, right? If they're subtracted, this is a little different, but it's what you think should happen. Just remember, if I'm subtracting all of this, what do I have to do? Distribute that negative throughout, right? So this is A minus C, and then it's going to be B minus D. Just distribute the negative and combine your like terms. And then the one that is the most difficult is when you multiply complex numbers. So what do you think you're going to have to do here when you multiply? Well, this is a binomial times a binomial, so you're going to have to distribute, okay? Multiply the first ones together, outsides, insides, and last. You're going to distribute. So here we go. We've got some operations with complex numbers. So the first one, again, is pretty quick and easy. If I'm told to add those complex numbers, then I'm just going to add the real parts. So what is negative 2 minus 4? It's negative 6. And then the imaginary parts, positive 3 and negative 9. That is negative 6i. So the complex number would be negative 6 minus 6i. Just combine the real part and combine the imaginary part. Now for B, it's a little trickier because you're subtracting the second complex number. So I would go ahead and recommend distributing at the very beginning. Now if I rewrite that, that's going to give me negative 1 minus 5i minus 3 plus 2i. Now once I've done that, it's just combining. Combine the real numbers. Negative 1 and negative 3 gives negative 4. And then negative 5i plus 2i, that gives negative 3i. Now then, letter C, 2i times 3 plus I. So again, I'm just going to multiply, but I got to multiply the 2i by both terms. So I'm going to multiply the 2i times the 3 and the 2i times the I. So 2i times 3 is 6i. I was testing you. I didn't think it was 3i. Okay, and then 2i times I is 2i squared.
-2.
Okay, but we talked about earlier, I squared is equal to negative 1. So that is going to be 6i plus 2 times negative 1, which simplifies to be 6i minus 2. So if you want to rearrange that, you can. I don't know how picky the computer's going to be if they make you do the real number and then the imaginary part. I really don't think it is. I think they'll take it either way. All right. Okay, then D part, we've got 3i, and all of that is squared. So when you square a monomial, you square all parts of the monomial. So I've got to square the 3 and I've got to square the I. So 3 squared is 9 and I squared is I squared. Again, we just talked about I squared is negative 1. So that gives negative 9. Okay, here, letter E. I've got negative 3i and it's all squared. Okay, so again, square all parts. Negative 3 times negative 3 is positive 9. I squared is I squared, which we can rewrite as -1. So that gives -9
That's cool.
is my answer. Okay, then the last one are two complex numbers, which look like binomials, right? Two terms in them. Two complex numbers being multiplied, so we have to distribute. 5 times 5 is 25. 5 times 2i is positive 10i. Negative 2i times 5 is negative 10i. And then negative 2i times positive 2i is negative 4i squared. Now look what happens. 10i times 10i minus 10i goes to 0. And then I squared is the same thing as -1. So I can rewrite that as a positive 4. So I've got 25 plus 4, which is just 29. Now let's talk a little bit about that letter F. Look back at what's in parentheses. 5 minus 2i and 5 plus 2i. That looks like
Jesus.
the difference of perfect squares.
Even perfect square is what I'm trying to say.
Okay? Where you have the same terms in the first and the last and you alternate the signs in between them. So if I had a difference of perfect squares, it would factor down to be that. But does anybody know what it's called when you multiply two parentheses, then the only difference is the sign between them? We call those two parentheses a word. Starts with a C. I don't know if you've heard it.
Give us a hint.
Starts with a C.
When another one.
It ends with an S.
Cons.
Well, that's the right first three letters.
Connotation.
Consonants.
Constants.
B, C, D, F, G, H, those? No, not consonants. You're close. You're close, though.
Constants.
No. They're called conjugates.
Oh, I've heard that before. Somewhere.
Conjugates. Because when we get to dividing, we're going to be using that word. So I just want to make sure you went ahead and saw it. If I tell you to multiply something by its conjugate,
The same opposite side.
that means you change the sign in the middle of them. Okay? That's a conjugate. Because what happens when you multiply conjugates? The outside and the inside term go to 0 every time. That's what always happens. So they're useful for that reason. Okay, so if I've got an I to the 83rd power, what does that simplify to be? We're just going to keep writing that pattern over and over and over, right, until you get all the way to 83. No, you're not going to do that. God, that'd be awful, right? But that's one way you could do it.
Wait, can we use that?
Is it, is it I?
How did you get its I?
Because I divided by 4.
When you divided by 4, what did you get? You should get 2.
So it'd be 20.
Oh, because this way it goes in like, so it'll be like 0.25, 0.50.
So you get 20 with a remainder of
3.
3.
So then I just.
So whatever the remainder is, it's what it's equivalent to. So this is equivalent to I to the 3rd power.
Oh, I remember doing this a little bit. Not much, but.
And so I to the 3rd power is equal to -I.
That's something serious.
All right, so just to prove it to yourself, think about if I had to the 4th power and I divided by 4. That goes in there 1 with a remainder of 0. So what was I to the 0 power?
Shoot.
How do you know you need to divide by 4?
Because it takes 4 times before the pattern repeats. Remember that pattern we talked about at the beginning?
Yeah.
It starts over after every 4 times. So if I had something to the 5th power, you could divide by 4. That'd be 1 with a remainder of 1. So I to the 5th is the same thing as I to the 1st. If it was a 6, divide, remainder 2. I to the 6th is the same as I to the 2nd. Right? You can prove it to yourself if you want to go back and do that. That's how it works. Okay, then the last one, I to the -85th power.
1 over I to the 8. You did that or you not?
Yes. We hate negative exponents. They're just ugly. So we could rewrite that as 1 over I to the 85th power.
So these eyes follow the same rules as algebra.
Yeah, that's why you're in Algebra 3. So this is 1 over, then you take 85, divide it by 4. So that goes in there 2, 1 with a remainder of 1. So again, you can either do it my way, the old school way with a remainder, or you can use your calculator, right? If you get 0.25,
2. 1.
it's a remainder of 1. If you get 0.5, it's a remainder of 2. 0.75, it's a remainder of 3.
Quarters.
Yeah,
Okay.
thanks. I didn't know. So this is the same thing as I to the first power. So we could rewrite this as 1 over I or I to the negative first. They're the same thing.
Oh, that is the same.
Okay, so look at this one. Division of complex numbers. It says the complex numbers a plus bi and a minus bi are called complex conjugates of each other. Oh, a little foreshadowing, right? I told you that earlier. Example 4, complex conjugates. Find the product of the given complex number and its conjugate. So now then we're going to be multiplying all these by their conjugate. So again, this is just building up to the division we're fixing to get to. So what would be the conjugate of 3 minus I?
3 plus I.
It is 3 plus I. So if I multiply something by its conjugate, what does that give me? 9 plus 3i minus 3i minus I squared. Well, we know I squared is negative 1. So that's going to give 10 as its answer. So what's the great thing about multiplying a number by its conjugate? You know the outside terms and the inside terms go to 0. So if you want to skip that, you can. Because that's always going to happen when you multiply by a conjugate.
What is?
3 times I was 3i. Negative I times 3 was net. The outside and the inside go to 0. That happens every time. That's the whole point of difference of perfect squares. Is the outside terms and the inside terms are gone.
Let me just write that again. I got this.
Okay, let's look at B. B, we've got 4 plus 2i. Well, what's the conjugate of 4 plus 2i? 4 minus 2i. And then we would distribute. 4 times 4 is 16. 4 times negative 2i is negative 8i. 2i times 4 is positive 8i. That goes to 0. 2i times negative 2i is negative 4i squared. So that gives 16 minus 4 times negative 1, which is 20. And the last one is negative I. Well, what's the conjugate of negative I?
Positive I. Add
It is positive I. So that's going to give negative I squared, which is equal to negative negative 1, which is equal to positive 1. So right here we're going to divide some imaginary numbers now. So we want to write each quotient in the form a plus bi. So I am dividing 8 minus I over 2 plus I. That's no good.
Multiply by the congruent.
Yes, we are going to multiply by the conjugate of the denominator.
But is there a y?
Yes, you'll see why. What happens when you multiply by the conjugate? We don't have an imaginary part anymore, right? It's gone away every time. So now my denominator is just going to be a real number, not a imaginary part. So we know how to divide by a real number, but we can't divide by an imaginary part. So what we do is,
There's no way to, or there's no way to divide by imaginary?
yeah, this is how. We multiply by the conjugate.
I get what you're saying.
Just like when you learn to divide by a fraction, what did you do? Multiply by the reciprocal. So is there no way to divide by a fraction? Yeah, you multiply by the reciprocal. That's the best way to do it. So to divide a complex number, you multiply by the conjugate.
Okay.
Now again, you pick the conjugate of the denominator, and you have to do it to the numerator and denominator. Quick review, why? What is 2 minus I over 2 minus I?
1.
That's 1. So I'm multiplying something by 1. I'm not changing its value, I'm just changing its form. right? Because if I multiply anything by 1, it doesn't change it. So, let's multiply. Let's look in the numerator. 8 times 2 is 16. 8 times negative I is negative 8I. Negative I times 2 is negative 2I. And then negative I times negative I is positive I squared. That's over. Now 2 plus I times 2 minus I, that's going to give 4 minus I squared. Right? Because the outside terms and the inside terms are going to go to 0. They're going to cancel each other out. So now, the next thing I do is I replace my I squareds. So that's going to give 16. And now, look, I've got some like terms here too. Negative 8I minus 2I gives negative 10I. And then I squared is negative 1 over 4 minus negative 1. So that's going to give 15 minus 10I over 5, which we can write as 3 minus 2I.
You can divide by all things by 5.
Yes.
I'm just going to go.
Is that a 5?
Yes, that is 1 over 5 minus 4I. So if we multiply by the conjugate would be
5 plus 4i.
5 plus 4I. So 1 times 5 plus 4I is 5 plus 4I. And then the denominator, we're multiplying conjugates. So 5 times 5 is 25. Negative 4I times 4I is negative 16I squared. So that gives 5 plus 4I over 25 minus 16 times negative 1, which gives 5 plus 4I over 40. So that is 1/8 plus 1/10I.
Is it not 41?
41.
Yeah, 41. It was a test.
It was testing us, yeah.
You passed, Kelsey. Way to go, nerd.
Yeah. So that's going to be 5 over 41 plus 4 over 41I. Just like I said the first time. Okay, so I've got 3 minus 2I over I.
Multiply by negative I. Right? Yes.
Correct.
Which is really just.
So we're going to multiply by negative I. So that's going to give negative 3I plus 2I squared over negative I squared. Okay, now replacing, that's negative 3I plus 2 times negative 1 over negative 1. So that's going to give
Whoa.
negative 3I minus 2 over 1, which I'm just going to rewrite that as negative 2 minus 3I, flipping the order around. Okay, so now we're going to rewrite some of these. So let's look at A. The letter A is the square root of negative 8 plus the square root of negative 18.
2I times 32, right?
You want to just make it radical negative.
Yeah, so watch. So I know what you're going to have to do. This is going to be I radical 8 plus I radical 18. And now you're going to have to put those in your calculator.
No, you can just make
I know what I can do. They're going to have to put them in their calculator. So yes, 8 is 4 times 2. The square root of 4 is 2I radical 2. This is 9 times 2, so that is 3I radical 2. Yes, I know how to do them. Yes, I'm thankful you know how to do them. They're going to have to put them in their calculator. So this is 5I radical 2 or 5 radical 2I. That's going to be